In this section, we'll discuss equilibrium and free energy as it relates to an electrochemical process. The Gibbs free energy, delta G0, for a redox reaction under standard conditions can be found by using the equation delta G0 is equal to minus N times F times E0, where N is the number of moles of electrons transferred, F is a constant, the Faraday constant, and E0 is the cell potential, the standard electric cell potential. Now, under standard conditions, we know we have a temperature of 25 degrees C, 1 atmosphere, and solutions that are 1 molar. And Faraday constant is 96,500 calories per mole, or 96,485 joules per volt mole. Okay, here is a Gibbs free energy problem, practice problem 1. Given these two half reactions, determine the electric cell potential and the Gibbs free energy for the transfer of 6 moles of electrons. So we're given two half reactions with standard reduction potentials. So first we need to balance and arrange these equations so that the electrons gained in one are used in the other, right? So I flipped the first equation, the aluminum equation, and that's because it has the most negative reduction potential, meaning it's going to undergo oxidation. So we need to show it losing electrons. So I flipped that. Then I multiplied the top reaction by 2, multiplied this by 2 after flipping it, multiplied this one by 3, so that I had equal number of electrons gained and lost. Okay. Now, we said several slides back that electric cell potential doesn't change with the quantity. So it doesn't matter that we have a different number of moles of electrons here, or moles of reactant and product. That reduction potential doesn't depend on the amount. And also, we don't have to change the signs of the voltage because we deal with that later when we talk about the cathode minus the anode. So even though I flipped the reaction, I leave that standard reduction potential as negative because, again, that's the potential as if it were being reduced, and that's how we use it in our cell potential equation. Continuing on with this practice problem, now we need to find the cell potential, the potential of the cathode minus the anode. So the cathode is where reduction occurs. So here's the cathode, here's the anode, and we just need to subtract them. 1.065 minus negative 1.676, and let's see, 2.741 volts. Okay, now that we know the cell potential, we need to find delta G for the reaction using our equation minus N times F times the electric potential. So try to do that, and then I'll show you the solution. So here's our Gibbs free energy equation. We have a negative, we have 6 moles of electrons that are being gained and lost. Faraday constant in terms of volts, which is what we have our electric cell potential in, so 96,485 joules per volt times moles of electrons, times the electric potential, which we calculated in the previous slide, was 2.741 volts. And we get a delta G of negative 1,587 kilojoules. So you get times 10 to the third of that when you multiply these together, but we write it in terms of kilojoules. All right, let's walk through a second Gibbs free energy practice problem. Given these two half reactions, determine the cell potential and Gibbs free energy for the transfer of 11 moles of electrons. So I'm given two reduction reactions with reduction potentials. The first thing I'm going to do is rearrange and balance the half reaction so that I'm showing oxidation and reduction of equal numbers of electrons. So I'm going to do two things to this top equation. First, I'm going to flip it because this is the oxidation reaction since it has the smallest reduction potential. So I'm going to flip it and I'm going to multiply it by 2. So it shows a loss of 4 electrons. Okay. And then the second equation I can leave alone. And then on the next page, I will calculate the cell potential. So given these two half reactions, determine the cell potential. So the cell potential, remember, is just the potential at the cathode minus the anode. In this case, because the oxidation is happening here, this is the anode. So the cell potential is just that of the cathode, or the 1.23 volts. Finally, given the complete reaction, which you see there is the combination of the oxidation and reduction reaction, determine delta G for the transfer of 11 moles of electrons. So try that on your own, and then I'll show you the solution. Delta G is minus NFE, so 11 moles times the Faraday constant times the cell potential that we found in the previous slide, 1.23 volts, is negative 1.30 times 10 to the 6th joules. The negative value of that delta G shows that this is a spontaneous reaction. Hydrogen and oxygen brought into contact with a spark to start the reaction come together to form water, releasing significant energy. This energy is also released when carbohydrates are digested in biological systems, fueling life. Carbohydrates are formed, capturing that energy by the process of photosynthesis, which converts sunlight into chemical energy by driving this reaction in its opposite, non-spontaneous direction. This is the basis for life on the surface of the Earth, so it's very important. We can now store energy in the form of hydrogen gas by using electrolysis to run this reaction backwards, as we'll talk about later in the presentation.